All right, so today we're looking at continuity. Okay, so we'll define continuity using limits. Okay, so there's a couple different types of continuity. So the first type of continuity that we'll look at is continuity at a point. Okay, and so a function is said to be continuous at a point A if the limit as x approaches that point A of f of x is equal to f evaluated at that point, so f of A. Okay, and so we've got this continuity checklist. So in order for f to be continuous at A, then the following three conditions must hold. And this is that they all three have to hold. Okay, but we have to have that function has to be defined at that point. The limit at that point has to exist. And the limit at that point and the function at that point have to equal each other. Okay. Graphically, we can see this a couple different ways. So, for example, that would be continuous. Something like this would be continuous. Something like this. Even with the sharp points, it's still continuous. Okay, or like this. All right, those are all continuous functions. And so then we've got different types of discontinuities. So our first type is called a removable discontinuity. Okay, and so that's just a basic hole. Okay, we're traveling along our function and we've got this big hole right here. Okay, so that's a removable discontinuity. One way to think about it is that you've removed a piece of the function out. Okay. Another type of removable discontinuity is if you've got a function with a hole, but it's filled in somewhere else at that point. Okay, that's still a removable discontinuity. Okay, so these are both removable discontinuities. So any type of hole. Then we've got a jump discontinuity. Okay, so if we're traveling along on our function and if the two limits on either side don't equal, okay, that generally means that we've got a jump discontinuity. Okay, and so anything where we've got just a break in the graph like that. And then our last type of discontinuity is an infinite discontinuity. And that would be when we have a vertical asymptote. Okay, so for example, we had a vertical asymptote like this. Okay, that would be an infinite discontinuity. You could also have, if you had a horizontal asymptote, it's possible to have an infinite discontinuity there as well. No, it's not. Because you can still have a function defined there. Okay, you're just looking for where is the function not defined. All right, so if we define these a little more formally, so a removable discontinuity at a point x equals a is one that disappears when the function becomes continuous after defining this point. So basically there's a hole. That's what it means. The jump discontinuity is one that occurs whenever both of our limits from either side exist, but they don't equal each other. Okay, so our graph is approaching 2 different points. And then a vertical discontinuity or infinite discontinuity happens when f of x has a vertical asymptote. Okay, because the function is not defined for whatever the point where the asymptote is. Okay. We'll do some examples of discontinuities in class. Those are kind of the general, those are the main 3. And a graph can have more than one. So for example, we could have something that's like okay, where we would have removable discontinuities, and we also have a jump discontinuity. Okay, so you can have more than one. So those are general discontinuities. We can also look at the continuity at endpoints. So if we're looking at the continuity at an endpoint, so the continuity at an endpoint, so if a function is continuous from right or is right continuous at a, if the limit as x approaches a from the right is equal to f of a. Okay, and it's left continuous. So if it's continuous from the left at b, if the limit as x approaches b from the left of f of x is equal to fb. Okay. So one way to think about this is if for example, our function here would not be left or right continuous, or it wouldn't be continuous from the right or continuous from the left, because both of our endpoints are open circles. But if we filled those in, then it would be both left, or both continuous from the left and continuous from the right. Okay. We can also look at continuity on an interval. So continuity on an interval is when we're looking at just a specific interval of the function. And so if it's in order to be continuous on that interval, then it has to be continuous at all the points in that interval. And if the interval contains endpoints, then continuity on that interval means continuous from the left or the right at the endpoints. Okay, so some examples. We've got continuous on a to b. So if we're looking at a function on an interval a to b, okay, we're continuous from a included to b. And so this one would be continuous continuous from the right. So it's continuous on this interval or at this endpoint, but not left continuous. Okay. And then we could have the other way. So we could have continuous on a to b. Okay, same thing. an open circle inside of A, closed circle inside of B, and we can have continuous, oh, wait. Okay, that should be a closed bracket because we're including B. And then lastly, we can have continuous on A to B, where neither of the endpoints are included. Okay. You can also have where both endpoints are included, but that's kind of a general case, so we don't point that one out as much. Okay. All right, so looking at some examples. So we might be asked to determine the interval of continuity for a function. So they're asking us, what intervals would it be continuous on? Okay. So one way to think about this is graphically, another way is just looking at the functions. So if I'll graph it just so you can see. Okay, so our function here would be continuous on this interval because a polynomial is always continuous. And it's continuous on the second interval because a line is always continuous. So in this case, you're going to have two intervals where it's continuous. So we'd have it continuous on the intervals on negative infinity to 0, which is included. Sorry, no, yes it is. My graph is wrong. This should be a closed circle down here. This should be an open circle up here. But we're continuous on that interval from negative infinity to 0, and it can be continuous on 0 to infinity. Okay, so we stick an and in here, but you don't union or combine these intervals. Okay, if I can say nothing else about this, do not combine them or try to union them in any way. Okay, because if you do that, they're not continuous. If you union them, you would be saying it's continuous for all real numbers, and it's not because of this jump discontinuity. Okay, so when you're listing these, you list them using commas, okay, or just pop an and in the middle, but don't combine them. Okay, so then we're looking at, we can do this algebraically. So if we're determining whether the following function is continuous at A, so we're looking specifically at this point to see if it's continuous at A. Okay, so the first thing to check is whether or not A is in the domain. Okay, so the only thing that would cause issues would be our square root here. So our domain is, that has to be greater than or equal to 0. So 7 has to be less than or equal, or x has to be less than or equal to 7. Okay, 4 is less than or equal to 7, so that checks out. All right, so then we can compute f of 4 and the limit as x approaches 4 of f of x. All right, see if they're equal. So computing f of 4, we get 4 squared minus 7 minus 4, 16 minus root 3. And then we can compute our limit as x approaches 4. So it's the limit as x approaches 4 of x squared plus root 7 minus x. And I can just plug that in. So we also get 16 root 3. Okay, so because these are equal, then it is continuous at x equals 4. Okay. So if you're checking to see whether or not it's continuous at a specific point, make sure you check that that point's in the domain. Then you'll check to see if these two things are equal. And if all that's true, then we're continuous at that point. All right, and then we've got some continuity rules, just basic. If we've got two functions that are both continuous at a point, then these following operations will also hold continuity. Okay, so if we do any of these following operations, then the function that we get will also be continuous at that same point. Okay, so if we add those two functions or subtract them, if we multiply one of them by a scalar, we multiply them together, we raise one of them to a power, and lastly, if we divide them, given that the denominator won't equal 0. Okay, so if f and g are both continuous at a point, then the following operations will respect that, and it will still be continuous afterwards. Okay. And we've got for polynomial and rational functions. Okay, a polynomial function is going to always be continuous. A rational function is always going to be continuous except for when the denominator is not 0, or except for when the denominator equals 0. Okay, so same way we would check domain. That's exactly the same thing. If we're doing function composition, okay, then we want to check continuity. Okay, if we've got a function g that's continuous at a and a function f that's continuous at g of a, then we can put g into a, or f composed with g, and that is going to be continuous at a. Okay. The limits of composition of functions. So if g is continuous at a and f is continuous at g of a, then we can pop the outside function, and the limit of the composition is equal to f of the limit of the inside function. Okay. And then one other way to look at that is if we know the inside function's limit and is equal to a point, and we know that f is continuous, the outside function is continuous at that value, then that same limit property holds. Okay, so that's two different ways to think of that. Then we've got continuity of a function with roots. So if you want to take the root of a function, so square root, cube root, if it's an odd root, so like cube root, 47th root, then the function is going to be continuous at all points. If it's an even root, then that root of the function is continuous at all points where the inside is greater than 0. Okay, again, that is the same as with checking domain. Okay. A lot of these are very, very similar to domain. Okay, and then we've got continuity of inverse functions. So if a function f is continuous on some interval and it has an inverse on the same interval, then its inverse is also continuous. Okay. So if you've got a function that's continuous and it has an interval, then the interval is continuous. Or sorry, the inverse is continuous. All right, and then the continuity of transcendental functions. So all of our trig functions, they're all going to be continuous. I guess I shouldn't X that, but all of our trig functions are continuous. And then our exponential and logarithmic functions are all continuous. Okay, that's just kind of a general rule. You should know that those are continuous. All right, I promise we are almost done with this video. All right, so last couple of examples. So if we're looking, so we might be asked to determine the intervals of continuity for a function, and so we'll use our theorems just depending on what the function is. So for example, we've got a rational function here, so we use our theorem about rational functions. So we know that a rational function is continuous for all the x that don't make the denominator 0. So we'll set the denominator equal to 0. So we know that can't equal 0. And we can't factor this, so we'll plug it into quadratic formula. So we know that x can't equal 1 plus or minus 1 minus 4 times 1 times -1 over 2. So we get 1 plus or minus root 5 over 2. Okay, so our intervals of continuity for our function is all the intervals are all real numbers not including this. So we would list our intervals out, -infinity to 1 minus root 5 over 2, 1 minus root 5 over 2 to 1 plus root 5 over 2, and 1 plus root 5 over 2 to positive infinity. Okay, so those are our three intervals where a function is continuous. Okay, we can also be asked to determine the intervals of continuity for this. So we see we've got function composition. Okay, so sine of x is continuous everywhere. And then the square root of sine of x is continuous when sine of x is greater than or equal to 0. Okay, so sine of x being greater than or equal to 0 happens on the intervals, so it'd be 0 to pi. So if we're looking at the unit circle, so it's continuous on this interval from 0 to pi. And then it wouldn't be continuous on the bottom half, but then it would be continuous from 2 pi to 3 pi. Okay, and again, so then 4 pi to 5 pi. So it's always just that top half of the interval, and it keeps going. So we write that as from 2k pi to 2k plus 1. Okay, where k is 0, 1, 2, all the way up to positive infinity. Okay. All right. Sometimes you might be asked to redefine a function so that it is continuous everywhere. And if that's the case, then we'll notice, so this, we've got a rational function, so we'll try to factor it. Okay, so you're just trying to rewrite it so that way you don't have a denominator, so it's in a form that is continuous everywhere. For rationals, you're going to want to just try to rewrite it to cancel something. So g of x factors into x times x minus 2, x plus 1 over x minus 2. Okay, and g of 2 does not exist. Okay, we can't plug 2 in there, but we can factor this and cancel, so we get x times x plus 1 for x not equal to. Okay, so our x not equal to 2, so our redefining is g of x is equal to x times x plus 1. Okay. All right, And then our last thing in this section is going to be the intermediate value theorem. I know you're probably thinking this is a long video. I know it's a lot of information. So if you need to rewatch it, you can. All right, so we've got the intermediate value theorem, last theorem for this section. So if we've got a function that's continuous on an interval from a to b, and L is some number that's in between the y points for our endpoints. So let's draw a picture. I've got a function that's continuous from a to b. Let me draw that so I've got more room. From a to b. Okay. And L is some point, so we've got f of a, our y value for that one, and f of b, our y value for this one. Okay, so L is some point in between these two. So then there exists at least one number, C, that's in between A and B, such that f of C equals L. Yeah, this should be a C. Okay. Something to note though, it is important that our function is continuous on the interval from a to b, because if it's not, then it doesn't hold. Okay, and it is possible to have more than one. So we can have more than one. So if I've got a function like this, from a to b, f of a, f of b. Okay, and if I've got this is my L value, then I can have more than one C values that this could be equal to. Okay, that's okay. You just can't have it not be continuous. So if it's not continuous on the interval, so for example, if we had something like A to B with this break, then if we chose L, there's no point. So if it's not continuous, then there's no guarantee that there's a function wherever we choose the L value. Okay. All right, so we'll do an example. So one way you might see problems is that if we want to show that a function has a root or an x-intercept using the intermediate value theorem. Okay, so we've got our function here. We know it's continuous. Because it's a polynomial. Okay, so then we check our endpoints. So we do f of 0 is equal to 4, we plug 0 in, and f of -1 is equal to 1 to the third plus 4 times -1 plus 4 is equal to -1. Okay. We can just pick most of the time they'll give you the interval in these problems. So this one, I'm just saying let's use these two numbers. So since we know that f of x is continuous on -1 to 0, and f of -1 is equal to -1, and f of 0 is equal to 4, then by the IVT, or the intermediate value theorem, then there exists an let's say a C, stick with the definition, such that C is in between 1 and 0, and f of C is equal to 0. Okay, because we know that 0 is in between our outputs, so then there's some value that's in between our inputs that's equal to that C, or to 0. Okay. All right, so that's this video. I know it was a lot. We'll talk about it in class some. And if you've got questions, you can ask me then or email me.